All right, so for the remaining problems here, there's 20 left. Some of them you can skip, actually. Like these, they don't come into play until the next section, so those shouldn't actually be on here. I will show you the property. It is Pythagorean theorem. We've done Pythagorean theorem. So that is Pythagorean theorem, c squared equals a squared plus b squared. That gives you a right triangle. But it can be also used to identify acute and obtuse triangles. If you had c squared less than a squared plus b squared, it is then acute. And if you had c squared is greater than a squared plus b squared, it would then mean that it's obtuse. But again, don't have to do those problems, so I'm going to skip them. Going on to the back. 74. All right, this was using our two formulas. We had our formula to find altitude. It is going to be geometric mean of part 1 and part 2. And then to find a leg, it's the geometric mean of the adjacent part times the whole. And when we say adjacent part in the whole, we're talking about the hypotenuse there. So now, for 74, all right, we need to find x. That's the altitude, so we're using the altitude formula. So x equals square root of 3 times 9, part 1 and part 2. 3 times 9 is 27, so we get the square root of 27. Base perfect square that goes into 27 is 9. So we're right back where we started. Square root of 9 is 3. The 3 stays under. And our answer is 3 radical 3. For y, y is one of our legs. So we're using the other formula. 9 is the adjacent one to y. The whole, those two added together is 12. So we have 9 times 12 is 108. Square root of 108, again, it's not a perfect square, so we'd have to reduce. Biggest perfect square that goes into 108 is 36. So 36 times 3 is 108. Square root of 36 is 6. Again, 3 stays under, so that one's F. For Z, again, that's a leg, so use the leg formula again. Z equals the square root of 3 is the adjacent part this time. 12 is still the whole. That's going to be 36. 36 is a perfect square. Square of that is 6, so that answer is J. All right, down to 45. On 45, describe the triangle above, circle all that apply. Well, if this is 140, subtract that from 180, and this would be 40. That's 160, this would be 20. And then 60, this would be together, that's 60, subtract 60 from 180, that's 120. Those are 3 angle measures. So, describe the triangle above, circle all that apply. It's not acute. Obtuse would work because it has one obtuse angle. Right doesn't work. Equilateral doesn't work. Scalene works. All the angles are different, therefore all sides have to be different. Isosceles. If we don't have 2 angles the same, we can't have any sides the same, and that is not even something that matters. All right. On this one, there's actually no answer to this. So it says represent a line that is parallel. No answer. None of these graphs are parallel because you need a slope of negative 1/3. So first, this one's out, it's a positive slope. This one's a negative slope, but this is a negative slope of 3. This one's a positive slope. This one, it has a negative slope of 1/3. But in order for it to be parallel, we need to have a different y-intercept than the original line. This has the same y-intercept of 4. So this is the same line. So that one looks like the best choice, but it also doesn't work. We would have needed something parallel to that line and did not go through 4. So same slope, but different y-intercept. So there's no answer on 76. On 77, this was a flowchart proof followed by a 2-column proof. It's the same proof. So we just had to fill in the reasons, if we know that these are right angles, then they're congruent because all right angles are congruent. Yep. So let me go ahead and mark that on my figure as well. Then this was given. This one was not given, but angle ACB and angle ECD, those are vertical angles. So we know those are congruent by vertical angle theorem. Vertical angle theorem. So now we have three parts. All right, let me go ahead and label this other one that was given to us, AB and DE. So we have two angles and a side. That is not the included side, so two angles and a non-included side, that's AAS. We know these are congruent by AAS. What's the statement for their congruency statement here? Well, they gotta go in corresponding order. So ABC corresponds to EDC. All right. Once you know that the triangles are congruent, all the corresponding parts are congruent by CPCTC. So then it wants you to put these into the two-column proof. Again, you do the same order. So the slight things could be slightly different than this, but I could say that this is 1, this will be part 2, this would be 3, this would be 4, this would be 5, and this has to be 6. Now, really what has to happen is these two would have to be the last two in that order. These have to be 5 and 6. 1 and 2, these two have to follow that order. This one followed by this one. Other than that, you could have done any other order for 1 through 4. These two just have to be this one first, followed by this one, because we don't know this until you say that they're right angles. But this is just the order I would have put them in. But again, many different things would have worked for the two-column proof. All right, 78. The following conditional statements are true. Which of the conditional statements below have converses that are also true? So if we were to switch these around so that the then is now the if and the if is now the then. If a figure is a square, then it's also a rhombus. If a figure is a rhombus, then it's a square. That's not always true. That one doesn't work. On this one, if a triangle has 3 congruent sides, then it has 3 congruent angles. Well, that's basically the definition of a triangle. And anytime you have a definition, those should be biconditional statements. No matter how you write it, it's true. So if a triangle has 3 congruent angles, then it has 3 congruent sides. That's all true. That's good. Actually, sorry, I said definition of triangle. Definition of equilateral and equal angular triangle. On this one, if 2 angles are complements, then the sum of the measures of 2 angles are 90. All right, that's true. Again, that's basically describing what a complement is. This, again, is a definition. If I reverse it, it is true. If 2 angles sum is 90, then they are complements. So 2 and 3 are the correct answers. On 79, what is true about the conditional statement below? If an object is a pentagon, then the object is a polygon. Well, are all pentagon? No, is that so? That's a true statement. But then is the converse true? No, because not all polygons are pentagons. So that's not true. It is sometimes true. It's not never true. It cannot be determined. No, it can be determined because polygons can be pentagons. They just don't have to be. So B is the correct answer. On 80, produce a counterexample to show that the following statement is not true. So we need something that fits the first half of it, but doesn't work in the second half. So if a number is divisible by 2, then it's divisible by 6. So essentially, if you can find any number that's divisible by 2, but not divisible by 6, it would be a counterexample. So 8 would be a counterexample. Because 8 you can divide by 2, you can't divide it by 6 and get a whole number. Again, there's lots of counterexamples. On 81, in the graph below, the graph is shown. It wants to reflect across the x-axis. So, across the x-axis. It wants to know the y-coordinate of the point at -3. So, at -3, the original graph is here. It's 1 unit down from the x-axis. So, it'll be 1 unit up. So, it's at y equals +1. That's it. All right, on 82. It just says classify each. It doesn't say give a function notation or anything. If you wanted to be really specific, this is a reflection over the line, y equals 6. But you could just say reflection. Again, if you want to be really specific, over y equals 6. On this one, this is just a translation. Translation. If you want to be really specific, it's going down 1, 2, 3, 4, 5, 6. Down 6. Or if you wanted to do the other notation, again, but really, translation is all you need. The first one, reflection, was all you needed. On this one, it's a rotation. Again, that's all you need. If you want to be really specific, it's around the point at 10, 9. How many degrees? Well, this would be going clockwise. Sorry, count. Wait, which one is the... Oh, I'm sorry. Shaded is the preimage. So on this one, it actually went up 6, not down 6. So this one rotated this way. So it's going clockwise 90 degrees. Or you could say negative 90 degrees. Either one works. All right. 2 more pages, almost there. On this one, again, don't have to say anything. It just says classify. This is a dilation. I want to be specific. It's getting bigger, so it's an enlargement by, and then you'd have to list the scale factor. So the bigger image is 2 to 1. It's increasing by 2. So that's it. All right. Again, you really just had to say dilation, though. On 84, in the figure below, the dashed figure is the pre-image, the solid outline is the image. What is the transformation rule? Again, different ways that you can state this. I'm going to do it in function notation. So the pre-image was the dashed figure. So we went this way. 1, 2, 3, 4, 5, 6, 7. Oh, I went way too far. Not 7. Sorry. To here. 1, 2, 3. And then we went down 2. So that's a negative 2. So we went x plus 3, y minus 2. And that's it. On 85, draw a 180 degree counterclockwise rotation of the figure below and identify the new coordinates. Again, when you do 180 degrees, what you have to remember about that is the x and y values just both get negated. So negative x, negative y. You don't actually have to draw it. I would probably figure out the points first and then draw it. So for P, this point is at negative 5, positive 1. So that means that its new point would be at positive 5, negative 1. For Q, that point is at 4, 3. So then the new point would be at negative 4, negative 3. For R, that coordinate is at 0, negative 2. So the new coordinate should be at 0, positive 2. So if you wanted to graph the new one, now we have the points and it'd be much easier. So I have a point here. I have the point at negative 4, negative 3. And I have a point at 5, negative 1. And then connect the dots. On this one, it says that this bisects this angle. So this is again from our last chapter. 8 over 12, those two have to be proportional to these two. 6 over 9. You could do a lot of reducing here. Oh, it just wants to know, does it bisect? So are these two equal? Let's see. 8 over 12, that reduces to 2 over 3. This also reduces to 2 over 3. So they are equal, therefore they're proportional, therefore that is an angle bisector. So, yes. Determine the value of x. Same concept as up there, but we're actually using it to solve. You can reduce this side. That'd be 3 over 2. Cross multiply. That's 18 equals 3x. Divide by 3. X is 6. All right. On the next one. Again, same idea. We have an angle bisector. This one's a little more challenging. Doesn't matter which one you solve for first. Once you know one, you just subtract it from 10 to get the other. But we have to solve it in terms of one of these variables first. So let's put y in terms of x. So we'll have the 10 minus x for that piece. Because now we can set up a proportion. 5 over 8 equals x over 10 minus x. Cross multiply and solve. 8x equals 15 minus 5x. Bring the 5x over by adding it. That gives us 13x equals 50. Divide by 13. 50 divided by 13. 3.8. I'm going to round it off at 5. So that's this piece. 3.85. That's x. And then y, you just have to subtract it from 10. So, minus 6.15 for the other one. So those are our two answers. All right, on 89, below is the value of x in the figure. Or what is the value of x in the figure below? X is in this angle right here. Well, if these two are parallel, that means these would have to be congruent. So that'd be 70. This is now an exterior angle to this triangle. So this one has to equal the sum of the remote interior angles. So add those two up and we have x. So x will equal 5 plus 70, which is 105. Again, there's lots of other ways you could have done that one, but that's just one method. 90, we haven't covered that yet because this is using 30, 60, 90s and 45, 45, 90 triangles, which is in our next chapter. So that won't be on the test. All right. On 91, it tells us that they're similar. It wants to know the perimeter of the bigger one. So first, figure out the perimeter of the small one. So we have 42 plus 42 plus 45 plus 36. So this perimeter is 165. We don't have to find every single side because you can use the same scale factor for a perimeter as you do with the sides because they're all single dimensional measurements. So on this one, this side is related to that side up there. So I'm going to write that in a ratio, 48 over 36. And then I'm looking for the perimeter of that one. We got the perimeter of this one. Cross multiply and solve. So 36x. If you wanted to reduce, you could. These are pretty big numbers though, and I'm just going to end up plugging them into the calculator to see what it gives me. So 48 times over 36. I'm going to plug that whole thing in. 48 times 168 divided by 36. 224. All right, last one. In the figure below, this is the dilation of that. What's the scale factor of the dilation? I just pick a side that's easy to count. So we want to make sure we do image over pre-image. So I'm going to count the side. 1, 2, 3, 4, 5, 6. This is 6 units long. This one, 2, 3, 4, 5, 6, 7, 8, 12 units long. So we have 6 over 12, which reduces to 1/2 or 0.5. So either 1/2 or 0.5. And that's it. That's the review.